Hi everyone, welcome back to another remote session for statistical models. Today we're going to continue our talk about multiple linear regression and model selection techniques. So last time, as a quick reminder, we talked about backward selection, forward selection, best subset selection as some different approaches for ways you can select your model, select predictors for your final model. And I briefly mentioned at the end this technique called cross-validation. So as I was mentioning before, best subsets is great if you don't have a large number of predictors. Forward and backward selection methods, though, and stepwise, can be more useful and actually can be implemented even if you have an extremely large number of predictors. So those can be often helpful when you have this sort of big data type scenario where you have many explanatory variables at your disposal. Cross-validation is a technique that is very generalizable and flexible. It is a way to sort of see how well your model might do on unseen data. It's not like a perfectly unbiased picture of this, in that it will make it seem like your model will do a little bit better than we actually think it will for unseen data, but it's a good way to compare two different models without having to use like the stepwise approach that can potentially miss predictors along the way. So this is not discussed in the textbook. It's a little bit of a more advanced technique, I guess, in a way, but I think the idea is fairly straightforward, and hopefully you have a clear picture of it after I talk about it here for a bit. So the main idea is that we use a portion of the data that we have to fit our model, and then the other part of the data to test or evaluate how well our model is doing. So this model that we use to actually fit our predictive model, our regression model, they call training data, because we're training our model, getting it ready to predict things in the future. And the test set, or the evaluation set, is what we use to see, okay, how well do we expect this model to do on data that it wasn't fit on, data that wasn't used to fit or get the regression estimates here. And so overall, what this allows us to do is, if our model fit on just the training data does very, very well at predicting observations in the test data set that it wasn't used for fitting, then we can expect it would do pretty well in the future, assuming like a random sample. So this is like a great way to get a better understanding of how well we expect our model to do in the future for unseen data, which often is the goal for these predictive models. And so there's different types of cross-validation that are defined by the number of folds that we're using. So the number of portions that we split the data up into. One of the most commonly selected number of folds is just 5-fold cross-validation. So specifically to proceed using 5-fold cross-validation, what we do is we have our full data set, and we begin by randomly dividing that into 5 groups of the data, 5 subsets of the data. So they're completely distinct. They're separate subsets of the data, but together, their union, together they make the whole complete data set. We train the model using just 80% of the data, so 4 of these 5 subsets of the data together, we train our model on, and then we compute an average prediction error when we try to get predictions for the 20% of the data that was left out, the one subset out of the 5 subsets that we left out. So that's on the test set that we're getting predicted values for. Okay, and so there's 5 different parts of the data that we can leave out, 5 different fifths, or a 20% portion of the data. So we can repeat this process for each one of those pieces using a different test set each time. And then we can get the average prediction error across those 5 different folds. And the idea is we want the model that has the smallest average prediction error. We want the model that does the best when it's predicting data that it wasn't fit on. So I know this is a very new concept relative to other stuff we've covered in the course so far, but again, I think it's important because it's such a useful way to fit models in practice. And this idea of setting aside some data to fit a model and then setting aside the rest of the data to evaluate our model is just a very important concept because, again, it's so generalizable to other types of models. So we're working with regression models here, linear regression models. But you can think of, there's many different types of models that we just don't see in this course or that we have yet to go over in this course. Models that predict categorical outcomes, such as will somebody take an action or not? Will they buy this item or not at a store? Models such as that, or models with ordinal outcomes. So an ordinal variable is like a categorical variable, but there's ordering to the levels. So maybe a rating for like a Netflix title is a good example of an ordinal outcome. So the ratings are like 1, 2, 3, 4, or 5 stars. It's not really a continuous outcome, so that would be like an ordinal outcome, and there's specific types of models for that kind of data. So anyway, this idea of using cross-validation where we set aside some data for training and then some for a test set or evaluation set can be applied to all these different types of models. So understanding this concept of how this works is important, I think, and very useful. Like I mentioned, so the goal with cross-validation is that we want to pick the model that does the best on predicting values for our test sets, our portion of the data that was left out when fitting. And the idea is that this will prevent overfitting rather than just modeling noise in the data. We want to be modeling that true signal that's there. So there's lots of great R packages for implementing this. I found one that had some of the most succinct code, although it's not necessarily the package I use when I fit these models. I like to use a package called Glmnet that was made by some people at Stanford, and it's really awesome. They have a nice website that walks you through how to use it. But this function from this DAG package, DAAG, is, again, like really short. The code's really short and clean, so I thought this might be better for showing in class if you guys want to try out fitting a model using cross-validation yourselves. So, for example, we have a final project at the end of the year where you get to analyze some data, so maybe you'll want to use cross-validation to fit your models, in which case this code might be hopefully useful for you to use. So here we're looking back at this example on the high school graduation rates for different states in the U.S., and we're looking at these different predictors: population, income, illiteracy, and area of the state. And it's a little bit cut off here for this model. Oh, wait, no, we're excluding area from this model. So we want to compare with population, income, illiteracy, and area. Is that better than population, income, and illiteracy? So as we can recall, we could use a nested F-test since Model 2 is nested in Model 1. That would be an option. And again, not wrong, it's just a different way to select a model that would be based on more statistical theory. But we could use five-fold cross-validation here. So we can see how well this first model does in terms of its average prediction error on the test sets versus this second model. And also, again, we could use, best subsets, not best subset approach, because these are different size models. They have a different number of predictors, but we could use like stepwise regression to see if either of these models would be selected or not. Okay, but using cross-validation, we're going to use this CV linear model function, CVLM, from the DAG package. So you'll have to install this first, probably, if you try and run this. And I'm specifying M as 5 for 5-fold cross-validation. So this is the number of folds. And you can do up to the number of observations in your data set. That's the maximum number of folds, because your test set has to have at least one observation in it. So you can't have more folds than number of observations, because you wouldn't have unique test sets anymore. There'd be redundancy there. All right, and so hopefully this visual might be helpful for what's going on with cross-validation. So here's an example of 5-fold cross-validation. So let's say we have like our full data set that has, say, 100 observations. Okay, typically what we've seen so far in this class is we just use this whole data set for fitting our model. We just fit the full model on this. But with cross-validation, what we're going to do is we're going to randomly select 20 observations here for fold 1 and use that as our test set. And then we just fit the model on the rest, on the blue here, using 80 observations. And then we do that each time with a different chunk of the data. Okay, and typically like the 20 observations are randomly selected from throughout the whole data set, not like contiguous ones. That would be bad to do, but this is just for a visual demonstration. So this is just 5-fold cross-validation. So we get each of these folds, and then what we do is once we fit a model on the blue, on the training data, we can get predicted responses for the test set data, and then we can see how much we're off by on average. So using that CVLM function from the DAG package, we fit a 5-fold cross-validation for model 1. And here what we can see is on the x-axis is the predicted values for the test set, and on the y-axis are the actual observed values for the test set. So we can see, ideally what we'd want is we'd want to be able to perfectly predict the test set. So we'd want like a line right through the origin where we predict 45 and the actual value is 45, stuff like that. So here we can see that our predictions are not surprisingly imperfect, and that we don't perfectly predict the test set every time. However, there certainly is a positive, sort of decent correlation between our predictions and what the actual values were. So the model seems to be doing decent. Another thing to note from this plot is how you can see the lines here, like the red line, the dotted pink line, the dotted green line, are representing the model fits, the estimated regression equation. So we get a different one for each fold. For each fold, we have a different set of training data that was used to fit our model. So we have a different set of predictions and a different estimated regression line. And that's okay, because we don't use cross-validation to, it doesn't directly give us our final model. What we're doing with cross-validation is we're seeing which model does the best in predicting the test set. And then once we've answered that question, then we just go back and fit that model on the full data set. So that's another important concept. We don't actually use the model that we fit just on the training data as our final data set, as our final model. This is just allowing us to evaluate how well the model does relative to others, and then using that set of predictors essentially. And then we go back after we've determined how well it does on the test set. Then if we picked this as our final model, if it did the best among all candidate models considered, then we fit it on the full data set in the end. Okay. And here's the set of predictions on the x-axis by the actual test set responses on the y-axis here for the second model. So it's not really clear from the plot which one's better. There's not a super clear winner here yet. But we can get the MSE, the mean squared error, so the average error for the predictions for the test set for each data set. And so here's where we get a more clear answer. So the second model had a mean squared error of about 36, whereas the first one had a mean squared error and MSE of about 38. And we want to minimize MSE for our model across the folds. So we select model 2. So here's a great example of where model 2 had one less predictor than model 1, so it was less complicated, and thus had a smaller R squared itself. But it achieved this smaller MSE across the cross-validation folds. So that suggests model 2 would do better on predicting unseen data in the future. So again, this is sort of an interesting way to select a model, and it's very generalizable. So I think it's quite useful. So moving on from this model selection discussion, we can also revisit identification of influential or unusual points. So specifically, we're going to be looking for outliers and influential points here. And as a reminder, an outlier is a point that has an exceptionally large residual or error value. In other words, it's really big in magnitude. So residuals can be negative or positive, but just one that's really big in magnitude, really big in size, is considered an outlier. And informally, it's going to be a point that's really far away from our estimated regression line, from our predictions. Influential points are a bit different. So these are points that have a large impact on our estimated regression equation. And typically, these are points that have an extremely large predictor variable x, or an x that's far away from the average explanatory variable value. These have much more potential for being influential. But it's not always the case that every point with a extreme explanatory variable is influential. And we'll look at it a little bit. We'll discuss that a little bit more, how there's a weird exception to that rule, but in general, that typically is the case. So looking at outliers again, here is a plot where we're looking at people's age and then the number of times they visit the doctor per year. So as people are getting older, they're visiting the doctor much more frequently. This is a good example of a point that is not influential, but it is an outlier. So that's right here, this guy right here. So x, our explanatory variable, is people's age in years. And this point is right pretty much in the middle of those. So it's going to be very close to the average age. So it's not far away on the x-axis in either direction. But what it is far away from is it's far away from our estimated regression line here, which is in blue. And so what we can see is that here the blue line is fitted with this point still included, this outlier. The red line is fitted with it excluded. We can see that this point actually didn't change the estimated regression line very much. The slope is nearly the same, and the amount it shifted up is a tiny bit, but not much at all. So it didn't have much influence. We can actually see visually how this point did not have much influence on the difference in the estimated regression line. Okay, but an influential point, so here looking at a different example, we have the amount of coffee someone consumes and then their heart rate in beats per minute. This point over here is really far. It's an extreme value in the x-axis. It's an extreme explanatory variable value. And so it's very influential in that it's pulling the blue line. So the blue line is fitted with this point included. And then we can remove it and then refit it, the regression model, to the data, and we get the red line. So this single point, despite all the data being over here and sort of having this trend as the red line is showing, this single point pulled the regression model all the way down. So it has a lot of influence. And that's not good because it changes, by doing this, the single point changes all these predicted values pretty drastically in a lot of areas here on the plot. But as I mentioned before, not all values with an extreme, observations with an extreme x are influential. So if this point were up here, say, instead, so we can imagine this line sort of, I don't have red here on my thing, but this line like continuing. We can imagine if this point were instead up here, like this, okay, it would still be on the same trajectory that the rest of the data was. It still has an extreme x value here, but it no longer would influence the line very much because so it pulled the line down away from the trend of the data here, but here, if it was out here, it'd be sticking with that same trend. So the line wouldn't actually change that much. The estimated regression equation wouldn't change that much, even though this point is has an extreme explanatory variable value. So it would not be influential in this case. This is not an influential point. But this is because it changes the line drastically. So it's an important concept. Hopefully that's clear. So another aspect of data points that can be concerning is leverage. So leverage is extremely similar to influence, but again, not the same. So that point that I just drew earlier had high leverage because it had an extreme x value. And so here we can see actually there's this formal equation for leverage where we have sort of this, for the ith data point, its leverage is given by this. And this numerator here is representing how far away the x value is from the mean explanatory variable. So that's like the bigger this is, the bigger or farther away that point is in terms of the x-axis from the center of the data. And then it's standardized by the rest of the data here. So again, a point with high leverage can be influential, but not necessarily. And the reason it's an H, they tend to use an H sub I to denote leverage, is because actually you can get these leverage values out of what's called the hat matrix, which is just this matrix that you can use to multiply the data by to transform it into predicted values. It gets a little bit into the linear algebra of how regression works. But just as an aside, this is H because it stands for hat, because this is representing the spot in the in the ith row and the ith column of the hat matrix is this leverage value. So not important for this class though, but just wanted to mention that. So a typical leverage would be 2 over n, where n is the number of observations. So if it's much bigger than that, then it might be concerning, and you might consider removing it and then refitting your model, depending on what your goals are. So again, I wanted to emphasize the difference between leverage and influence. So influence is all about how much it affects our estimated regression coefficients. But leverage is just about whether we have extreme independent variable or explanatory variable values or not. So lots of times they do coincide, but they can, again, there's exceptions to the rule. There are high leverage points that are not influential, but nearly all influential points are high leverage. So the reason we care about these is because they affect our hypothesis tests. They can potentially violate a lot of those assumptions, that the errors are IID normal, for example. If points are highly influential or extreme outliers, then lots of times that normality assumption, the IID normal assumption, is not valid, which invalidates confidence intervals and p-values for our regression model. We can always still fit a regression model no matter what. Nobody's going to stop us from doing that. It's just our statistical inference might not be valid anymore. And also our predictions for future observations, for future data might suffer a bit. If we have these single outliers or influential points that have a lot of influence in changing the predicted values, that can cause our predictions to be worse. So they might be of importance to remove. And sort of like I was just talking about, influential points affect these predictions, can make our predictions worse, but high leverage points will make our estimated error variance smaller, which affects hypothesis testing, involving like confidence intervals and p-values. So, but people have, not surprisingly, proposed a workaround for this problem of observations potentially being problematic. So sort of like we have that leverage values to assess that, the HIs, we have these standardized residuals. So for the ith data point, we calculate it in this way. So it's the regular residual, the observed value minus the predicted value for our data set. But we standardize it. We divide by the standard error of the regression, and then this function of the leverage value. So this is another metric or another value we can use to assess if an observation is considered an outlier or not. And so this was a standardized residual, very similar name, but a slightly different formula. We have this studentized residual. And so this, again, we have the just the typical residual in the numerator. And then in the denominator, this time we still divide by this standard deviation of the regression, but we calculate it when we remove the ith point. So we fit the data, we fit the model on all the data except for the ith observation here, and then we get this new standard error of the regression each time. Okay. So just another metric that we can use. A really large studentized residual flags a potential outlier here. And formally, what people do, sort of like comparing the p-value to 0.05 rule, there's not like one cutoff that makes it an outlier or not, but typically people say they're concerned about a residual or an observation if it's standardized or studentized residuals exceed like plus or minus 2 or 3. And again, if that happens, if you have a point that's potentially concerning as an outlier, we can just try removing that and refitting our model. Sometimes that'll drastically change our model, in which case it was potentially a good thing to remove it. Other times it might not change the model fit that much at all, in which case maybe we'll just keep it in anyways. As sort of a note on this, in general, we want to not remove data points from our data sets when possible. Especially, it depends on context, of course, but especially in like public health settings where maybe you're assessing how well a certain intervention is working in terms of public health outcomes, or say monitoring. For example, we looked at an example in one of my public health classes about like the Flint water crisis, and they were monitoring lead levels in the city, and some observations got removed because they were considered quote unquote to be outliers. But obviously, you need to have some, especially in a setting like that where you're monitoring public health based on things that can have a huge impact on people and their lives. You need to have very, very good justification if you're ever going to remove an outlier. Even, no matter how extreme it is, you need some really strong justification if you're just going to handpick and remove data. And in general, that's extremely frowned upon. It's considered very bad practice because you could just be removing it for bad or nefarious reasons, for ill-intentioned, bad-intentioned things. But obviously, it depends on the setting. If you're trying to predict basketball game scores, you can go ahead and remove whatever points you want. Handpicking that's not a big deal. But again, it depends on the setting. So something to keep in mind if you use these models in the future. So Cook's distance is another metric we can calculate for our regression model. So this again is used to assess how influential a point is. And so it's a sort of complicated function of the studentized residuals squared, and then the leverage values here, and k, the number of predictors. Sort of an ugly looking formula a little bit, but it's commonly used. People tend to say if this Cook's distance value is between 1/2 and 1, then the point is moderately influential. But if it's bigger than 1, then it's considered very influential and might be cause for concern. And sort of interesting, this Cook's distance was proposed by Dennis Cook, who is a professor at Minnesota here, University of Minnesota, and he's still in the statistics department, actually. So this has been around for decades, I think, this Cook's distance measure, but yeah, kind of interesting. He's still there teaching. Okay, so moving on from assessing points to being potentially problematic, I wanted to revisit coding up of categorical predictors. So I talked about briefly before in one of the slide sets about how R is using an indicator variable underneath, or a dummy variable they call it. Essentially, it creates a vector of zeros and ones, recodes the data as zeros and ones to make a categorical predictor into sort of a numeric type thing that can be used for fitting a regression model. But we only saw categorical predictors that had 2 levels. But you can, in general, include predictors, explanatory variables that have more than 2 levels. So we're going to look at an example with this Palmer Penguins data set again. So you guys are already familiar with this a little bit. I've shown this in a couple of our activities, I think, and maybe in one of the slide sets already too. So we have these measurements on these different species of penguin. So we have many measurements on penguins within the same species, but I just showed 3 measurements here, one for each species. So we have this Adelie penguin species. I might be pronouncing these terribly wrong. Gentoo and chinstrap penguins. So we have lots of different stuff recorded on these penguins, like their bill length in millimeters, their flipper length in millimeters. And so yeah, so it's an interesting data set. Here we can see in this data set we have roughly 350 observations or so here. Looks like 344 maybe if you add these up. So we have 124 measurements on Gen 2 penguins, 68 on chinstrap penguins, and 152 on Adelie penguins. And here's a picture someone made of these penguins, so it's kind of neat. Someone took the time to record all these things on these penguins and then put it together in this data set as a good example for regression modeling, where maybe you have a categorical predictor here, like their species. So here's a picture of the chinstrap penguin, Gen 2, and the Adelie. So they all look a little bit different, and maybe have different dimensions in terms of their bills and flipper lengths and such. So so we're going to look at an example of modeling their bill length. So this graphic that was included on the GitHub page, this person's website that they made for it, shows how this was measured for the different penguins. So again, we're going to be looking at how we can predict what their bill length should be, using different factors about the penguins, such as their species and flipper length, stuff like that. So we fit this regression model where we're predicting bill length. We're going to use just species and flipper length, where there was 3 different species, by the way. Again, so we can think about how will this regression output look? What will be the predictors that are listed in the regression output here? So we know we're going to have flipper length, but what's it going to look like for species? We've already seen this in class where we have a categorical predictor, but I wanted to sort of talk about it more in depth. So here we have the 1 row for flipper length like we expected, so that's not surprising. For species, we have 2 predictors, 2 explanatory variables here. So we have this Gen 2 indicator and then this chinstrap indicator. And if you notice, what is missing? So we're missing that Adelie penguin species level. There's no indicator for Adelie species. So actually, in general, thinking about what R has done here, it made indicator variables for the different levels of species at Gen 2 and chinstrap. But there's only the number of indicators is equal to the number of unique levels of the categorical variable minus 1. So in this case, it was 3 minus 1 equals 2. So we had 2 explanatory variables that were indicator variables here. The reason that is because Adelie, that species sort of gets absorbed into the intercept term here. In other words, we can still find the predicted value for a penguin that is an Adelie type penguin. We can get the predicted bill length. What we then do is just set species chinstrap is equal to 0 for an Adelie penguin, and species Gen 2 is equal to 0 for an Adelie penguin. Whereas for a Gen 2 penguin, species Gen 2 is equal to 1, and species chinstrap is equal to 0. We'll look at that a little bit more with I'll actually write out what these explanatory variables look like a little bit more. But here let's visualize why maybe we even want to include species as a predictor in our model. So I'm just creating a scatter plot here, and then I'm coloring it by the penguin species. And then I just changed the point type to be a solid circle. So here we can see, in general, it looks like the flipper length, as the flipper length increases, the bill length increases on average. And then what we can see is there's these very distinct distributions of the bill lengths depending on the penguin species. So here's all the Adelie penguins, chinstrap, and gentoo. So they're very separated. There's a clear separation in the data depending on species. So that's showing that it's a very important predictor in the model. This is extremely clear cut. In general, in real data, although this is a real data set, but typically you won't get this clean of a separation by the levels of a categorical predictor. So here it's very clear that species is important in modeling this data, but in general, it might not be always so clear cut. But anyway, so we have flipper length is our predictor here. And what you'll notice is that I drew the estimated regression equation for each species. I added that as lines to the plot. So for the gentoo penguins, for example, this is the predicted values, the predicted bill lengths for all the gentoo penguins based on their flipper length, which is different than the predicted bill lengths for Adelie penguins, represented by the blue line, given their flipper length. And what we can see is that these lines are parallel. Okay, they're perfectly parallel. And that's because the slope for flipper length, we go back to the regression output, is fixed at 0.215. So this regression slope here does not depend on species. Essentially, there's just a linear shift, a single number shift in the predicted value for whether a penguin's gentoo, chinstrap, or Adelie. And so here we can see that the shift is represented by the distance between these estimated regression lines. So for example, here the difference between Adelie and, the difference between chinstrap and gentoo looks like it's about like, that's maybe like 43, that's like 38. So maybe like 6 is the distance between chinstrap and gentoo. That's the vertical distance here. And if we look at the regression output, I'm sorry. I looked at the wrong thing. So we want to look at, because Adelie is our reference category. It's our reference level. So we want to look at the distance between Adelie, the blue line, and the gentoo, the red line. So here that's about like 3. Looks like that vertical distance between these two is about 3, between gentoo and Adelie. And so if we look at the regression output, we see that, yes, species gentoo is about 3, 2.857. And so this value here, this 2.857, is exactly this distance, this vertical distance between these estimated regression lines. So I just wanted to point that out, how you can visualize actually the effects of a categorical predictor in this way. Okay, and then thinking about, again, how this is coded, exactly what R is doing underneath the hood, I'm getting what we call a model matrix, a design matrix, based on our regression equation here, a regression formula. And then we can look at what this looks like. So this is what R is doing underneath. R is constructing explanatory variables, and it always does this in general. It just doesn't show it to us. Where for the intercept term, it just makes this all ones, all the way down for the whole data set. For the other penguins, for example, this first row is representing an Adelie penguin. And that's because the indicator for chinstrap is 0, and the indicator for gentoo is 0. So this first row is for an Adelie penguin. And then we have its flipper length measurement here, which got cut off a little bit. This second row is for a gentoo penguin, because the indicator is saying, yes, it's a gentoo penguin. No, it's not a chinstrap. And then the very last row is for a chinstrap penguin. And there's its flipper length. So this is sort of how R turns a categorical predictor into a numeric matrix, a matrix of numbers still. And it does this for the whole data set. And again, if we had another species of penguin, if we had a fourth species of penguin, then we would just have another indicator column for that particular species that would be zeros and ones. And notice that for a given row, it can only have one species at most. You can't be a chinstrap and a Gen2. It has to be exclusive. So sort of one way to sort of think about this from like a mathematical standpoint, where we formally define things, R is declaring that this species chinstrap variable is equal to 1 if species is chinstrap and 0 otherwise. And then similarly, for species Gen2, it's equal to 1 in the case that the species is Gen2 and 0 for all other cases. That's sort of how R is formally defining this. So a reasonable question you might ask is, why can't we just do species is equal to 0, 1, 2, where 0 is for Adele, 1 is chinstrap, 2 is Gen2, or maybe like 1, 2, 3. Why can't we do that? And well, you could, and you could fit a regression model in that way. But you would be, in doing so, you're sort of assuming this relationship about the data that's not necessarily true, and actually in reality is likely not true for these penguins or many other data sets in general. So if you were to code it in this way, what would happen is that you're assuming the effect of being a Gen2 penguin compared to being a chinstrap penguin. The difference between those is 1. You're assuming the difference between those two species is exactly the same as the difference between the Adele and chinstrap species, because their difference is also 1. 1 minus 0 is 1. 2 minus 1 is 1. So you're assuming this distance between them is exactly the same, the three different species. But looking at Adele to chinstrap, chinstrap to Gen2, that is certainly not the case. The distance between these estimated lines is not the same for all of them. Adele to chinstrap is this huge distance here, blue to green, and that's much, much bigger than Adele to Gen2, the distance from here to here. Or I'm sorry, the contradiction actually is that the distance between Adele and chinstrap, the blue and green, that distance is not the same as chinstrap to Gen2. So chinstrap green to Gen2 red. Yes, okay. So the distance from red to green is not the same as the distance from blue to green. But if you were to code species in this way, you would be implicitly assuming that and actually constraining your model to force that to be true. But that's not the case. So that's why it's better to code it as zeros and ones, which R does, fortunately for us, automatically underneath the hood. But this is sort of a helpful understanding for why we can't just do this in case you get more in-depth into regression modeling in general. Okay, and then here's just a quick citation for this Palmer Penguins dataset that we used. Someone went to a lot of work to put it together, so I wanted to make sure to give them credit. It's a really great, cool dataset to use. All right, and that's it for today. So I'll be posting the, I'll be talking about the midterm sometime this week. I'll send out an announcement. We'll have this take-home midterm coming up soon. But yeah, I'll communicate more information about that shortly. So thanks, guys, and I'll talk to you again soon.